What if climate repair worked less like a project and more like an operating system for the planet? In this course, we'll explore how AI, robotics, mineralization, sensors, and verification could work together to support continuous carbon removal and ecosystem restoration. This topic is a convergence point. The course began with autonomous intelligence, cognitive twins, trust layers, memory, governance, and new ways for humans to work with machines. Then it expanded into biosystems, robotics, habitats, agriculture, oceans, forests, and mobility. Module 5 added the missing substrate, programmable materials and energy systems. Now those pieces come together as a planetary repair network. Not one invention, but a coordinated system for sensing climate damage, directing autonomous action, powering interventions, and verifying results across many environments. This sets up the civilization-scale systems coming next. One useful way to understand this network is as a planetary immune system. AI and climate intelligence detect where carbon removal or ecosystem repair could have the highest impact. Then autonomous tools, drones, robots, vessels, and engineered materials move in to capture carbon, transform it, store it, or mineralize it safely. The work does not stop after deployment. Sensors, satellites, chemistry, and ledgers verify what actually happened. Over time, the network learns which interventions work best across forests, oceans, farms, mines, cities, and industrial zones, then improves the next response. The first job is deciding where action creates the highest return. AI scans many opportunity types at once: industrial emissions, carbon-rich wastes, degraded soils, coastlines, mine tailings, and basalt formations. It then layers in climate forecasts, satellite imagery, hydrology, soil chemistry, energy access, and biodiversity signals. The goal is not just maximum carbon removal. It is durable repair with co-benefits for water, ecosystems, and local needs. As new data arrives, priorities change, creating a living opportunity graph that guides where projects should start, scale, or wait. The climate repair network is a stack of systems that reinforce each other. The physical layer does the work, capturing carbon, mineralizing it, restoring ecosystems, and deploying robotics in the field. The intelligence layer decides where, when, and how to act, using models, simulations, and optimization. The observation layer measures reality continuously through sensors, satellites, drones, and computer vision. Finally, the trust layer turns results into credible evidence, with registries, audit trails, and transparent verification. When these layers connect, climate repair becomes an operating system, not a collection of disconnected projects. Carbon removal only matters if the captured carbon stays out of circulation for a long time. That is why repair technologies focus on conversion, not just collection. Sorbents, membranes, biochar, and reactive minerals can concentrate CO2, then move it into forms that are harder to reverse. Solid carbonates, stabilized soil carbon, alkaline ocean chemistry, or carbon locked into concrete. Each pathway has trade-offs. Direct air capture may be highly measurable, but energy intensive. Weathering and biochar can use less energy, but verification is harder. The goal is durable, traceable storage that fits local ecosystems. Climate repair becomes real when intelligence reaches the field. Ground robots can spread mineral feedstocks, rebuild soils, plant vegetation, and keep capture equipment running. Drones add fast eyes overhead, mapping terrain, checking restoration, dropping seed pods, and finding methane leaks before they grow. Marine systems extend the same logic into coasts and oceans, where they monitor chemistry, support kelp recovery, and protect blue carbon ecosystems. The powerful idea is coordination. Many small machines, guided by AI, adapting locally while scaling restoration across huge landscapes. The AI layer acts as the network's decision brain. It combines climate forecasts with soil, ocean, satellite, and industrial data, then asks 4 practical questions. Where is carbon removal most valuable? Which intervention is safest? What resources are available? And how confident are we in verification? Climate models flag stress, drought, floods, and ecosystem risk. Geochemistry models estimate reaction rates, permanence, leakage, and compatibility. Before robots act, simulations test the plan. After deployment, measured outcomes feed back into the engine, improving the next decision. At planetary scale, climate repair depends on evidence, not promises. The process starts with a baseline: carbon levels, soil chemistry, water quality, biodiversity, and land condition. As interventions begin, ground sensors track changes continuously, from CO2, flux to pH, and mineral reactions. Satellites, drones, and aerial imaging provide independent context, showing vegetation growth, land use change, soil moisture, ocean color, and albedo. Computer vision adds another layer by checking site conditions, robot activity, erosion, and infrastructure performance. Together, these signals feed verified carbon accounting, so results can be audited, trusted, and publicly reported. For climate action to scale, claims need evidence that others can inspect and trust. A removal event starts with provenance: where it happened, what method was used, which materials were involved, who deployed it, and when. Sensor readings, satellite data, lab results, and models are then validated before entering a distributed ledger registry. Once recorded, the outcome can become a carbon credit, restoration certificate, or public accounting entry. Because each verified outcome has a unique auditable record, it becomes much harder to double count, alter, or exaggerate climate benefits. Climate repair becomes far more valuable when it restores whole ecosystems, not just carbon balances. Reforestation, wetlands, kelp forests, regenerative farms, and watershed repair each remove carbon, but they also rebuild habitat, soil structure, water storage, and local livelihoods. I helps connect these efforts to the right place, where biodiversity corridors are needed, where floods can be reduced, or where drought resilience matters most. Monitoring then tracks living signals from species presence and soil health to water quality. The goal is a planetary health dashboard with carbon as one important measure among many. Now we can see the full loop. Maps where intervention can have the highest climate impact, then models which approach fits best: capture, mineralization, or ecosystem restoration. Automated field systems carry out the work and place sensors where evidence will matter most. Satellites and ground instruments measure carbon performance and ecological change. Verified results become trusted records, often tied to carbon credits. That evidence flows back into the AI, improving the next round of decisions and deployment. The same intelligence can adapt to very different places. Near factories, it can capture and verify emissions. In mines, it can lock carbon into rock or tailings for long storage. On degraded land, it can rebuild soil carbon, deploy biochar, and restore water cycles. Along coasts, it can monitor alkalinity, protect shorelines, and rebuild blue carbon ecosystems. The common thread is coordinated sensing, action, and proof. By 2050, the goal is not just more carbon removal projects. It is a connected accountability network for planetary repair. Carbon, water, land, food, and biodiversity have to be managed together, because each system affects the others. The key shift is from one-off claims to continuous verification. Satellites, sensors, transparent ledgers, and public reporting make outcomes visible and comparable. That changes governance too. Cities, companies, farmers, and nations can coordinate around shared evidence, not just promises. In this model, climate repair becomes part of society's operating system, always monitoring, adapting, and maintaining Earth's life support systems. Project 25 brings the module together as a closed loop for climate repair. I finds where action can matter most. Robots and programmable energy deploy interventions. Carbon mineralization turns captured carbon into durable storage. Environmental sensors measure whether ecosystems are actually improving. Distributed ledgers add verification, so impact claims become auditable, not just aspirational. The bigger lesson is that climate repair is not one technology. It is an intelligent planetary system linking carbon, water, land, biodiversity, and resilience. Module 6 builds from here into neuromorphic robots, tiny ML sensing, decentralized science, and future world systems.